What's up, everybody? Hope you're all doing well. Today we're going to be looking at the classic merry-go-round problem, and we're going to be applying rotational inertia and torque and angular acceleration to go ahead and solve this problem. So let's go ahead and dive right in. Alright, so here's a problem. We're going to have a merry-go-round, okay, and we're just going to set the radius of this merry-go-round to be 4 meters, and then it has a mass of 100 kilograms. And then we're going to have a child. They're going to be standing on not quite the edge, but they're going to be 3 meters from the center point as such. And then we're going to have Dad, who's going to be pushing on this with a force. I didn't say this, but we're going to assume that it's tangential. Oops, I didn't give you a force, did I? So let's just make it up right now. So let's say Dad pushes with a force of, I don't know, let's keep it simple, 120 newtons. And he's going to do that for 5 seconds. All right? And we're going to solve a number of things, and we'll just kind of go through it step by step. So the first thing we want to know is the rotational inertia of the system. Now we're going to treat, for simplicity, we're going to treat the merry-go-round as a solid disk. And the inertia equation for a solid disk is equal to 1/2 mr squared. And the child, well, for the child, just for simplicity, what we're going to do is first give this child some arms, and then we're just going to treat it as kind of a point mass. So a single mass going in a circle. Okay, so we're going to treat it as if all the mass was just located as a single point. And so for a point mass, the I for that is going to be just simply mr squared. So when we're looking for the system, the combination of the child and merry-go-round, we're just going to find those two and add them up. So the I for the system then is going to be 1/2. Let's do the merry-go-round first. Merry-go-round has a mass of 100, a radius of 4 squared meters, and then the child, notice the child's not on the edge, so their mass was, what was their mass? 30 kilograms, and they were at 3 squared meters. Alright, and so we'll just go and multiply that out and get our I for a system. And I get 1070, and the units for this is going to be kilogram meter squared. Alright, let's go ahead and do letter B. So letter B, we're now looking for the acceleration. So for this we're going to be using basically Newton's second law for rotations. So that means when we sum up our torques here, we're going to set that to I alpha. Now in this case, our torque is simply the dad pushing, right? So it's going to be the force from the dad, and we're going to say it's tangential or already perpendicular to the radius here. So we'll say, remember, torque is force perpendicular to the radius. So we're going to say that he's already pushing perpendicular. So we're going to go 120 newtons, and he's pushing on the edge, so that's going to be 4 meters. So this again was the I of the system. So the I of the system was 1070 kgm squared times alpha. Alright, do a little math, and you get 0.449 radians per second squared. So that's going to be the angular acceleration. Remember, that's how quickly we're accelerating in this direction. Alright, let's do the next two questions on a new page here. So the last two questions are dealing with velocities. So the first one is, what is the final angular velocity of the system? So we know alpha here, right? And then we're saying the time is 5 seconds. And we're going to assume that the omega initial is 0 radians per second. So we'll simply use one of our rotational kinematic equations to solve this. So we can use omega final equals omega initial plus alpha times time. So we got omega final equals 0 plus 0.449 radians per second squared times 5 seconds. This is a relatively easy calculation, right? Basically, radians per second squared means every second you're increasing by about 0.45 radians per second. So after 5 seconds, that would give us an angular velocity of 2.24 radians per second. Okay, so now we're looking for a linear velocity. So notice that the angular velocity, this is of the whole system, right? But that's the same no matter, these two things, the merry-go-round and the child, are rotating at the same angular velocity, okay? But the linear velocities are different. So the linear velocity of the child, let me label these C and D. The linear velocity of the child is simply going to be V equals R omega. Remember, however far away you are, the farther you are, the faster you're moving. So for example, if you had someone else hanging out on the edge here, they'd be moving faster because they're traveling the same distance in the same time, a farther distance in the same time, and therefore they must be going faster. So anyways, we'll go ahead and do this out. So the R of the child was 3 meters times 2.24 radians per second gives us a linear velocity of 6.72 meters per second. All right, hope that was helpful. Actually, you know what? Let me throw out a bonus question. You have this child on the merry-go-round, and let's just assume they're standing on here. They're not like holding on. So let's imagine there is no friction. If there's no friction, they would simply like slip off, right? They would just kind of move in a straight line and slip off. So my question is, what is the coefficient of friction, the minimum, we'll say, minimum coefficient of friction needed for them not to slip? Coefficient of friction for them not to slip. So this is a review question for you. So I do want to see, can you apply previous concepts to new challenges? So go ahead and maybe you can write the answer in the comments, and at some point I'll respond to them, but I want to give you a chance first. All right, hope that was helpful. I'll see you in the next one. Hey, if you're still there. The hint is going to be centripetal force. That's what keeps you from falling, right? Slipping. So use that to calculate. Good luck.